Okay, good morning. Thank you, Phil, for the very nice introduction. My talk is about capabilities, which is also a very, very old subject in computer science. And my aim is to make these capabilities both safe and convenient. So what do I mean by that? Capabilities are the context I'm in is essentially a mostly functional language. That's what Scala is, among with many other languages, for instance, OCaml. So we are a functional language, we have a functional culture, but we also have constructs for direct style side effects without unprotected with a monad. Unlike all the other languages that now have also all these functional features, like Phil said, they basically, all of them acquire them bit by bit. I think the difference is the culture. Are your basic collections immutable or mutable is, for instance, a very important distinguishing factor. And there Scala is firmly in the functional camp. Our collections are by default immutable. The style is immutable. Variables are generally looked very critical upon, but nevertheless they're sometimes used. Why are they used? Well, because they're convenient. Sometimes you just want to reach for this counter on the side that just counts invocation, or a generator for some new symbol which is different from each other's, and sometimes it's just very convenient to essentially put this thing on the side to, let's say you have a complicated accumulation operation with several things. Yes, you could write a fold, but the fold is clunky. It's just more convenient to use a little variable here and there. So they're convenient. But on the other hand, they are looked critical upon because used widely, they're definitely not safe. There's a whole problem of essentially tracking problems that have unrestricted aliasing. So that's a very hard problem for an analysis, and probably just as hard for us humans. And it gets worse when you go multi-threaded, because then essentially all your aliases translate to race conditions, which are among the worst problems you could have in your program, because they manifest themselves as at the most inconvenient times in unpredictable fashions usually. So that's the dilemma, that we have these things, and yes, they are convenient to use, but they're not safe. So we have this uneasy choice that, do we want to be convenient and also, let's face it, with injecting a little bit of mutability can make programs faster. So do you want to be convenient and fast but unsafe, or do you want to save but maybe more complex and slower? And Scala programmers in particular, they do like their guardrails. We want to essentially be protected from misuse of features that maybe others introduced in the code base, or you introduced in the code base half a year ago, and now you wonder, well, what idiot did this? And often I find it was myself a year ago. So the problem is that a language's job is to encourage good code. So it's also essentially a social aspect of language design to say the language should be there so that people are driven to produce good code. So ideally, a program that looks simple on the surface is also safe and predictable. But with effects, that's not always the case. Using effects can make programs shorter and also sometimes simpler to read, but used unwisely, harder to reason about. And that's a problem, because we are now used not just to functional programming, but also to types. So types are there to essentially keep us safe. And types, in the classical mixed functional paradigm, they don't talk about effects, and that's worrying. So one answer to that is monads, and it's a staged architecture of effects. And here I should have put a citation according to Phil, and that would have been the marriage of effect and monads of Wadler and Thiemann. So I'll do that in the next version of the slides, so then you can read it, but now I just state it. So the idea of an effect system is to say, well, let's pretend all you can do is in this white box where the lambda is. And you say, well, that's a purely functional language, and machines can do more. They can do error handling, they can do network communication, they have state, they have transactions, they have all sorts of other resources. But the machines, you can get at them only by constructing a program that interacts with the machine. So it's a staged architecture. The first stage is a pure functional program that produces the second stage that handles the effects. So what programs can do is in the white box, and what computers can do is in the light blue box, and what computers can do is much larger. So that's the current approach when you use a monadic effect system, like in Scala, Katz effect, or Zio, or a system like that. The problem with that is that it's not so convenient. You have essentially this uneasy choice to say, well, either I have a sort of God monad, like the I/O monad, that can do everything, and then in the case of Zio, it's parameterized with 3 parameters that I have to carry over everywhere, and then everything that can do, I can use, and nothing else. Or I'm more fine-grained, and I have essentially a monad per effect, but then I have the problem of composing these monads, which is theoretically possible. I mean, there's monad traverse and these sort of things, but it's sort of advanced programming, both to write and to read. So the other view would be to say, well, no, let's not pretend we have a sandbox. Let's pretend we can use the whole computer, so everything that the computer can do, our program can do, but we mitigate access to these things with capabilities. So basically, we have all these capabilities, the file system, state, errors, but to get at that, I need a key, and if I don't have the key, I can't get at that. So the safety is achieved by basically not handing out any keys to programs. That's how you interact with untrusted components. You say, you have an untrusted component, but you don't give it any keys, you don't give it any capabilities, so you know what it cannot do. So that's essentially the idea with access control with fine-grained capabilities. What I should say, what's sometimes misunderstood, is it also depends on the runtime. So one of the big benefits of the effect monad approach was that it could do things that computers couldn't do, namely asynchronous programming, multi-shot continuations, probabilistic programming, all these things. There's a monad for everything. And runtimes, native computer runtimes, can do some of these things, but not all of them. So native runtimes always could do error handling. Most of them had a thing like exceptions, but then often it stopped. So if you want to do the capability-based system, then essentially your runtime system has to be able to do directly what you want to do. But runtimes are getting better, so the big reason to use monadic effect systems was reactive programming, so essentially light-white concurrency, and there in particular runtimes are about to acquire them. So on the JVM, where Scala is strongest, there are now virtual threads that do the job. On Scala native, we have implemented native continuations, and even on JavaScript and WASM, there's now stack switching, which can do the same thing. So you can use continuations or something like continuations on Scala.js if you specify that you should use WASM for that. So it's becoming universal, this idea to have light-white concurrency everywhere, which means that the direct style approach using capabilities becomes more capable and therefore more interesting. So where does it all go back to? It goes back to a long, long time, to the first paper on object capabilities was by Jack Dennis and Earl van Horn in 1966. Interestingly enough, Jack Dennis was also a founding member of WG 2.8, the working group on functional programming. So there's a clear connection between the two strands, even though object capabilities have lived mostly, as the name implies, in the object-oriented world until now. So what's the idea behind object capabilities? It's that capabilities, they're just regular program values. They can be created, they can be passed to other object constructors, and they can be passed in messages. and that's all. And access to certain things is mitigated by holding a capability. In an object-oriented world, you can do this very easy to say, well, essentially, if I have a file, then the file itself is the capability. To invoke anything on a file, well, I have to hold the file object. I can't do anything else. So it's not a big overhead. I identify the objects I interact with the capabilities. The advantage of that is that it's very simple. There are no features. In fact, we are taking a feature away. What's not foreseen in this model is global mutable state. So that's a way to essentially hide capabilities. So it's appealing in its purity and simplicity. And at the same time, it's quite powerful. In particular, it's sort of the gold standard in security. So in secure operating systems or secure other things, capabilities is the gold standard. And there's more recent work like Cherry, which is a capability-enabled machine at Imperial and Cambridge. And that's essentially... But the problem is that capabilities, even though they are the gold standard in a way, they're not really very widely used. They're still sort of a bit exotic. So you ask yourself, well, if capabilities are so good, why are they not everywhere today? Well, the problem with capabilities is, first, that they are not that convenient. If you think it through, then if you want to pass a capability of everything you can do to every part of your program, you get very long chains of passing things around. You might have one leaf way down the call chain needs a certain amount, let's say 3 different things, then you have to pass down these 3 different things on every caller of this thing. So this can get tedious. You can have essentially a sea of passing around these capabilities. And there are ways to address that. You can, for instance, all bundle them up in a context, which is sort of the analog of a supermonad, of a God monad, where you say, now the context gives you everything, but that's then not very fine-grained. You can't really say precisely what you want to pass around. So that's the first problem with capabilities. The other problem is they could also be safer. So in particular, there's the problem of capability revocation. So once an object holds a capability, it can hold on to this capability forever. It can never be forced to give it up. It has the capability, it can just use it. And that could lead to an untimely use of an effect. You might want it to enable effects only in a certain window of time, and afterwards you want to say they should all be done by now, and you can't do that easily. There is an answer to that in the world, but unfortunately that answer uses state. It's basically you just foresee a switch in the capability where you can turn the capability off. So then the next time when somebody tries to use the capability, you get a runtime crash because the capability says, well, I'm no longer usable. But that's in a sense not an answer. We want a static guarantee that we use capabilities the right way, not essentially introduce arbitrary runtime crashes. So lifetimes are hard to enforce statically, and the other thing is also sharing. I'm going to talk about that at the end of the talk. It's also hard to enforce statically. So these are the problems. So the original object capability model was untyped, and a lot of the work has been done in untyped versions. For instance, there are languages like E based on Java. Actually, I had a little bit to do with that without knowing much. They asked me to write an E compiler. I didn't know what E was, but it was derived from my Java compiler, so I just wrote them as a little thing on the side, and then I learned, it's a capability language. I didn't know what capabilities were at the time. And then there were successors like Joey and things like that. But it was mostly weakly typed or untyped. Joey was more influential than E, and it was a JavaScript dialect. But in fact, it turns out that if you look at capabilities from a typed point of view, then you can get important improvements. So the first thing is that you can address this problem of passing too many capabilities by using implicit parameters. So passing them implicitly means you still have to declare the capabilities you need at each state, which is good. I would argue is good because that's essentially an important part of your contract. But you don't need to explicitly write the tedium of passing all these capabilities capabilities from where you have them to where the next call needs it. So that's implicit parameters are a great help here. And the second thing, and that's essentially our work, our current work, is that if we can reflect capabilities in types, we can make them safer. So that's the second part. Scala 3, that's the context of our work, is actually already well positioned as a host language for capabilities because it has two things, namely it has implicit parameters via using clauses, so you can pass capabilities without the boilerplate, and it already has path-dependent types, so it has sort of a lightweight form of dependencies where a type can refer to a program variable. And that lets us talk about these capabilities in types. We need more than that. That's not good enough, but essentially the basics is there. We have sort of a lightweight dependent type system, and that's what's needed. You need to be able to handle these basic dependencies to be able to do that. I had a very interesting discussion with Leo White and other people from the OCaml team who also have this challenge of essentially effects, and they have a mode system. And essentially we concluded that every language reaches out for the tool set that they do best. So we reach out to dependent types, and they reach out to something which is Hindley-Milner compatible, and they get we have two completely different solutions, but they're sort of predicated by what the language already offers. So in that sense, you can argue they are sort of the natural extensions of languages in this domain. Okay, I'm gonna just switch my slide deck because I have an easy thing. Okay, so let's talk about capabilities for effects. Before I do that, I just want to ask you some of your things that you probably meet daily. So one daily thing that you have to deal with is error handling. What's your favorite error handling scheme? Is it a sum type like option or either with pattern matching? Decomposition can be a pain. Yes, we're back. All right, let's start from the first thing. So what's your favorite error handling scheme? One choice is option or either using pattern matching directly. The problem with that is decomposition can be a pain. I have all these decompose with, well, is it a sum, is it a none, is it a left, is it a right, and these sort of things. So it's more convenient if we have a monadic bind, because then we can essentially shift the error case to the left and just do the things in the success path. But that works great as long as you have a single monad to deal with. Composition of monads can be a pain. Or you go back to the old exceptions, but then you have another choice to say, well, do you want checked exceptions or do you want unchecked exceptions? And no matter what your choice is, there are very good counter-arguments against. So essentially checked exceptions, even though they look appealing, nobody likes them in the end, but because they're just too clunky and essentially not flexible enough. And unchecked, well, unchecked is unchecked. You don't know what you throw, and your context, your contract becomes dynamic. Let me just put this. Okay. So the other question is, what's your favorite async computing scheme? So lightweight threads waiting for events. What do you do? One choice is callback futures, but that gives you leads you straight into callback hell. Monadic futures are better, but again, you have the problem that compositions with other monads can be a pain. So async plus error, yeah, maybe we should have a single monad for that. Or you have async await, which is sort of the more direct and simpler thing, but that's a very limited thing because it doesn't work with higher order functions. You can't await in a higher order function, so you have to all flatten out your program, which is not very convenient for us. Or you go back to coroutines, but again, that's a bit imperative. Then coroutines basically force you to use state in a way. So what I would like for errors, overall, I think I like something like Rust's question mark best, but I want something a bit more powerful that also works inside higher order functions and along the call chain. So here's something I would like to do. So here the task is you have a list of options and you want to convert it to an option of lists. all okay is the name of the function. And the way I want to write it is I want to say optional, so the whole thing is an option, access.map. I just want to have a little map, .ok. So optional in Scala 3 is just a function application. So it's the same thing as optional apply and then the body. So it's just syntax. So basically the optional is a function wrapper around the thing. And the .ok thing is like get, so it takes out the value of the option. But if the option is none, it would not crash, but return to the enclosing optional with a none value. And .ok should also work in arguments of higher order functions, such as you see here in the map. That's a difference to Rust's question mark. You couldn't write a Rust's question mark at this position, but I want to write an OK in here. Okay, so that's what I want to do. What would I like for async? Well, something very similar. So here we have the same thing, the await all method that takes a list of futures and returns a future of lists. And what I want to write is, I want to say, well, it's a future, and you go to your list and you map it again, but now you map it with await and not OK. So you say, I want to wait for each future, and once I have all the futures, I want to turn the result into a list, and that would be the result of the enclosing future. And that, like OK, also works in higher order functions, which makes it different from, let's say, await in most other languages. And it should, furthermore, also be usable outside future blocks. In fact, that's the same for OK, but for await it matters more. So I want to be able also to write await all like this, to say, I want to essentially take a list of futures and give you back the await, but I don't really want to wrap it into its own future, which would be its separate thread. I just want to say, well, I need an async context. That means basically some thread that can suspend, that comes from the outside, and in that thread, I would do these things. So async now is a type of a capability that allows to await. So here we see capabilities the first time. And using async in Scala 3 defines an implicit parameter, hence the capability is passed automatically. So that's nice that we can write just await futures, so we don't need to pass the second async parameter, because the compiler will synthesize one. If we are in an async context, that means we are either inside a future or we get the async from somewhere else. Okay, so let's now combine these two things. I said combining monads is hard. What about this one? So what I would like for errors plus async is really total kids play. I want to say, well, I want to return a future. It should return a result. So in this case, I have switched option for result. And it should do fs.map await OK. So I say, okay, for each of these futures, I wait for it, and I check whether it's okay. If yes, then I get a future. If not, then I get essentially an error in this result, and that would be the thing, the thing that I return from the enclosing future. So let's decompose that a little bit. What happens here? So I have two nested function calls, one future and one result. They're both apply methods in the existing modules of future and result. And then I essentially go through the list and I do await and OK. So if I look at this thing from the point of view of algebraic effects, then essentially this thing here would be a prompt, a boundary to which I return, and that, again, those two things are prompt, future and result. And await and OK are both an effect. So we see handlers, prompts, and effects in a way when we look at it. And the nice thing is we just follow the shape of the desired result type with the prompts. There's really nothing much to do. I want a future of results. I just write future, result, and I apply what I do. Compare with monadic programming, where I need at least one traverse here. And yeah, I mean, if I know a lot of category theory, then I find my way around. But it really is advanced knowledge, and it's also hard to read for somebody reading the monadic code. What the hell does this do? Here, it's completely obvious. Okay, so there must be, that's too good to be true, right? There must be some gun here. And in fact, there is a problem. So if we want to switch these things around, so now I want to say, I want to not convert a future of results into a list of future result into a future of result. I want to do it the other way. I want to have a result of future to result future list. So basically, I push it the other way around. So I want to write result, future, and this thing here. Looks just as easy as before, but does it make sense? No, it makes no sense, because here this result says, well, when I go through the list and I return and I find that it's not okay, I want to return an error here. But in the success case, I want to return a future. But I know this only after the future is already running. So here the result should return a future that when I wait for it will get running, right? So I can't just then, once the future is returned and waited for, I can't then simply change my mind and say, oh, no, I didn't really have a future. You get a none here. So this makes no sense. Right? So that's essentially the problem in a nutshell here, that it seemingly commutes fine, all these effects, but there are certain effects that shouldn't commute, like this one shouldn't commute. And we want the type system to catch that error. So the challenge is, can we find a type system that does that? So the 10,000-foot view is monads don't commute. Effects in general also don't always commute, but often they do, quite often actually. So capabilities as arguments do commute, so they're more convenient in that thing, but not all combinations of prompts make sense. So some of them are unsafe, and I want my type system to give me the commutativity by default, but flag an error when effects are introduced in the wrong order. And the idea here is we want to use capabilities to describe these effects. So if we do capabilities for effects, then the basic rules are quite simple. So here we see it in exceptions, which is a classical effect. So to declare an effect, I would write def function, and it returns some t, and it throws an exception e. And I can also express that using a capability alternatively. In this case, the function f would just return the t, but it says to return a t, it needs the capability that it can throw an exception e. So the effect on the right here moved to a parameter on the left, which is the capability. And in fact, that works literally in Scala. So t throws e is just a type, infix written infix, it throws te. And this type is actually a type alias for what we call a context function type. So it's a function from can throw e to t, which is applied implicitly. So basically, whenever I have one of these things, I will apply the function. So throws te expands to can throw e question mark arrow, which is this implicit application t. And that is morally equivalent to just passing a implicit parameter to the function itself. So that's just essentially going left and right from function parameters to function result. So all this thing is done. That's been presented in Foundations and Applications of Implicit Function Types in POPL 2018. But why? The question is, well, why does that matter? So what gain do I get by representing effects as capabilities? Isn't that just not just a game with symbols? In fact, it's more than that. So the effects have this fundamental problem, which is effect polymorphism. Unlike other types, effects are transitive. So if I have a long calling chain from F1 to Fn, and Fn does some effects like I/O, throw exceptions, assignments, await, or things like that, then the effects of F1 include all these effects down the calling chain. So they accumulate along the calling chain. And now if the call graph is dynamic, which happens when I have a higher order function, how do I describe the effects of F1? So that's the problem of effect polymorphism. And the point is that if capabilities support effect polymorphism very naturally whereas other techniques don't do that to that degree. So in current Scala, here's the signature of the map method in list. So it's defined in list of A. It takes a B and a function from A to B and returns a list of B, right? So if I wanted to add traditional effects, it would look like this. So we'd need a second type parameter E for the effect, and the function then is allowed to execute that effect. So the function would have this effect, and the same effect gets returned from the map. So this is not Scala syntax. There's no F. It's a hypothetical game. If you wanted to add effect polymorphism, that's one way it could look like. You might say that's okay, but it really isn't, because in a high-order functional language, and even more so in an object-oriented language, basically every call is a virtual call. Every call is a call to something that gets dynamically bound and that you don't know. So you have to introduce one of these parameters for basically every call you make. So you really get an explosion of these effect parameters. Another case in point is a little-known fact that actually Java supports syntax like that. You can have exceptions in parameters. Nobody does it because it's just too painful. So people use monomorphic exceptions in Java everywhere. So people don't even know that exists. So what about with capabilities? Well, with capabilities, that's what it looks like. You might say, what? That looks exactly the same as before. Yeah, it looks exactly the same as before. We don't need to change map one little bit. So why is that? Well, there's a trick to it. So this type A, double arrow B, is now the type of impure functions that can capture any capability as a free variable. And we introduce a new type, a single arrow B, for pure functions, which brings us finally, Scala finally, an alignment with Haskell, where we both use the single arrow for pure functions. So you could say, well, essentially Scala has waited all this time to become pure, and then they could finally use the good arrow of Haskell. So now we are finally at this point. Okay, so here's an example. How this is used. So I said the idea now is, instead of talking about effects, I talk about capabilities that I retain in these function types, what a function can do. And the nice thing is, because a function is a closure, right? It closes over its environment, so it can hang on to free variables. So I don't have to pass this capability through the type of map, because the function itself will already hang on to it. It will already have this capability, so map is not concerned. It just applies the function, and the function can have effects or not. Map is completely polymorphic to that. That's the nice part of it. So here's where we see this in action. So here we have a very simple thing, a user-defined method with file, and it should execute a body on a file that I create here. I create a log file, I run the body with this log file. After the body runs, I close the log file and I return the result of the body. It's a typical try with resources pattern, and here's how I can use it. I can say with file f, and then I write f.write OK, and that will write OK to the file, and the file will be closed. The problem, of course, is I might return from the f, because it's polymorphic, there's a type parameter. I might return a closure that accesses log file after it's closed, and then I have a problem. So here's the problematic thing. So what I could do is I can write with file, and I return you a lambda that when it's called, I said, I write to the file, I'm late. But of course, that doesn't work because the file is closed by the time this lambda will be called. So we want to rule that out. And we can do that by just changing one character of the body of with, in the signature of with file. I just write a hat here. So the hat marks this thing as a capability. And capabilities can't escape. So capabilities can't be returned from that. So we need to track them in the types to make sure that that's the case. And if we do that, then, and we try this bad program, then we get an error which says local reference leaks into outer capture set of type parameter of method with file. So the system rejects it. The error message could probably be improved. We're still fairly rough edges here, but at least you get an error. So that's something already. Okay, so I'm going to quickly talk about the basics of that. So the basic is that we need to track capabilities in types, and to that purpose we introduce this capturing type, which is a T and a hat and a set of capabilities. So T is a type and C1 is a capability. So what is a capability? In the object capability sense, a capability is just a program value, or in here, an identifier standing for such a value. So it's a program variable. But we don't want to track all variables in types, all free variables. We could, I mean, there are systems that do that for essentially optimization and things like that, but they would be very fragile. They would be very large and they would be very fragile because what you capture in free variables is an implementation detail. It's not part of your contract most of the times. So there are only certain things that we want to track, and others we want to say it's not the compiler's job to enforce any of that. So the way we do this is by essentially a meta-circular argument. We say a capability is a parameter or local variable that has as a type a capturing type that will itself capture further capabilities. So your capability, if you rely on other capabilities, which means at some point it must stop. So in this model there's a root capability cap from which ultimately all others are derived. So that's the system. So cap is sort of similar to object in an object-oriented system, or a top type or something like that. And then we have a little shorthand. So T hat, what you've seen is just a shorthand for T hat cap. So what we saw here with the file thing is to say, well, that's cap, so it could be, file could capture any capability. It doesn't really matter. It's just important that essentially the file that we pass in here is tracked as a capability. We don't specify what the precise thing is that it's tracked. So essentially the cap is the top capability, and is also the way to enable polymorphism on these things. For the function types, we have this thing that a pure arrow following with a capture set of capabilities is a shorthand for function type hat CS. So that's important because if you have long chains of curried functions, then otherwise the capabilities would bunch up at the end and you wouldn't know which one refers to which anymore. And finally, the A double arrow B is a shorthand for A arrow cap B. So that's what we see, and that's the impure function. Okay, so let's see, I'm going quickly over that. So what we did is we worked it on a language, but we also worked on a theory, on a calculus. And the first step on this calculus is simply type lambda calculus with capabilities. So here we have a version of simply typed lambda calculus, which is in so-called monadic normal form. So we add lets to it. That's actually quite similar to the thing that Phil saw on the whiteboard when he visited Karlsruhe for a completely different purpose, namely the formalization of lazy functional programming. Okay, but what we also have is our function types are dependent. We need to do that because they have parameters can be tracked as capabilities, and our types are both shape types, which are basically function types, or capturing types. So we have this hat and the capture set in the types. So that's essentially the very basic language we start with. What we need then is a sub-capturing relation. So we have a subtyping system, which for capabilities is very important because you have a natural subtype relation for the sets. If you have more capabilities, then that's a supertype of a type with fewer capabilities. Or other ways put, if you have no capabilities, then you're pure, and that's a subtype of any type that could do something. So subtypes that can do something, that have effects and capabilities, are supertypes. So smaller capture sets leads to subtypes, and pure types with empty capture sets are subtypes of capturing types. And subcapturing then is defined by the subset axiom plus this one, which is actually very important. So you say if we have a variable that has a capturing type in the environment, so it's defined like that, then we can use the capture set of the capability X, and that will be more refined than the capabilities with which it is declared. So here we have an example. We say f is a function that uses I/O, and g is a function that uses f and async. So what we have then is to say, well, when we have the capability set g, that is more specific than a capability set that can do f and async. That's what g was declared, but to hold the g is to hold less. So holding g doesn't mean you can do f and async. It means you can do just the g encapsulated is, so it's purer than that. But if somebody needs an F and async, then you can pass a G. Then the F and async is a subset of I/O and async because F gets widened to I/O here, and async stays alone. Okay, so if we plug the empty capture set into this capability, what we see that if X is just a shape type, so it's not a capturing type, then X, by this rule, is the capture set consisting of X subcaptures the empty set. So basically the whole thing is pure. So that means that that's essentially our justification that we can drop all types that are not capabilities from capturing types. We could write them, but they don't really contribute anything because they're subcaptures of the empty set. So variables of pure types can be dropped from capture sets. And then now if we look at simple typing, then I know there's a lot of symbols, but most of them are really just dependently simply type lambda calculus, simply type lambda calculus with dependent functions. So the capability stuff is underlined in gray. So we have this rule here that says, well, if X is a variable S capturing C, so C is the capture set, then the type of X is not S capturing C, but something more specific. It's S capturing X, because we have the X and we know X is now a more specific capability, so that's better. So that's the first thing, that as we name things, we can pull capabilities down, and it's very important because typically the C is cap. The C can be anything, and then if it can be anything, it can conflict with anything. But no, by essentially just naming this X, afterwards we talk about X, and X is very specific. Okay, then for the function type, we say, how do capabilities come into existence? Well, essentially, if we have a lambda abstraction like this one here, and then we look at the free variables of this T. So what are the free variables of the lambda? And we deduct the parameter X, and that becomes the capture set of the closure here. You see? And, well, you say that captures all free variables. Yes, but we can drop all variables which are pure, which are not capabilities, by the rule that I've shown you before. So this will, in the end, just capture the capabilities. That's all we need. And the capture set of a function gets discarded when we apply the function, because then the capabilities are done. They are no longer present in the result. Then we essentially what you see here is because the function type can be dependent, so Z can be in the result type here. So it means I need to do a renaming in the function application. So in the function application, if T2 contains Z, then it will be renamed to Y. And that's a reason why we restrict functions to just variable name to variable name, because that lets us do this renaming. We can't do a full substitution because our capabilities are not fully dependent types. We can't have a full term in a capability set. We can only have a variable. So we need to do this trick. And to make up for it, we introduce these lets, which essentially let you pull out a term from any context. And there you have the restriction that the locally bound variable cannot be contained in the result type, and you will use subtyping to essentially avoid it, to remove it. And then you have the standard subsumption rule, and that's it. Okay, so this is all fine and was known to us for a long time, but then there was this pesky problem of polymorphism. So can type variables range over capturing types? And I think I'm close to running out of time, so I will not go into that. I refer you to our paper, Capturing Types in Toplas 2023, that handles that. So that has, I think, essentially the only practical thing that works for polymorphism. So basically it works, it's something that is inspired from modal logics. It works with box types, but you won't see them because they're all inferred. So it's essentially, it's complicated, but the compiler does it behind the scenes. So, and it lets you, the captures tunnel through nicely from composition to decomposition. And it also explains why this with file problem failed with escape checking. Okay. So what's the current status, going back to the practicalities? So we are about 2 years into the 5-year project Caprice, which is called Capabilities and Resources for Effects. We have tried capture checking in the Scala 3 compiler itself. with the goal of do arena allocation of context. So capabilities, since they control lifetimes, they also let you do something like arena allocation or things like that. We have added capabilities to the standard library. We're about to release the full standard library with capabilities. Right now, it's the currently released part is just the collections. And we have a new library for direct style continuation-based concurrency and I/O, which is called Gears, which is also annotated with capabilities by now. So you can turn on capture checking in Scala 3.7 like this. So if you run in Scala CLI, you specify you want 370, and you want this dependency. So you need the capability-enabled library, because otherwise all the basic operations would drop capabilities. And then you need to turn on the import language experimental capture checking, and then you're set. I should warn you, it's still quite rough around the edges. It's still a research project. But the experience so far is that the notational overhead is actually very reasonable. And I'm going to show you that in the two next slides. So if we take, for example, the list API, so list is sort of the cornerstone of things, and you see what has changed from what we see so far, and actually basically nothing has changed. List is exactly the same as it was before. The only thing here is, well, now the double arrow, of course, means impure functions. Well, it meant impure functions all along, but now we have pure functions. So, and also there's this thing that some of these parameters get ahead because we say here we have this iterable ones, which can be an iterator or any kind of collection. And we say, well, this thing, when you traverse it, it could have side effects. I mean, it might have side effects in existing code. So we have to add the hat to essentially enable that. Otherwise, the thing would have to be pure. But there's no capture annotations in results, and otherwise everything is as it is. So what has changed? So what has changed is if you have a lazy collection, so a collection that you will run through only later on, like an iterator, then things will change. So for instance, the map function now has to say, well, I return an iterator, but the capabilities it hangs onto is the current iterator. So because when I call next on this iterator, it will need capabilities to do its thing. So it can hang on to the capabilities of this, and also of f. F is an impure function. It can capture capabilities. And of course, f will be applied by the map iterator, so I have to add this. Same thing for flat maps, same thing for append. So transforms of iterators get capture annotations, but other things, as long as things are strict, we're good. And that's sort of the secret why it works, because in practice, at least in Scala programs, I would say the case where I have a delayed effect, an effect in a closure, is about an order of magnitude or more less common than if I essentially do the effect right now. So essentially, I have a function, I give it a capability, it executes the capability, it's done. That's by far the most common case. And in the common case, we need to do nothing. That already works. So we only need to do something for delayed effect. And I would say, arguably, this is actually good knowledge. So if the iterator can do the side effect of the current iterator and f, I want to know about it. This is really important knowledge. So I think this is useful addition in the type system. Okay, so let me finish up. Let me just see whether I can switch. Is that on the screen? Yeah, okay, great. Okay, so switching gears and finishing up, what I've shown you is all capabilities about lifetime. But the thing we are working on now is to have capabilities that control sharing. And that is very interesting because it can exclude complicated global side effects. It can avoid data races, and it gives you fearless concurrencies. So capabilities need to mediate access to mutable data structures and enforce exclusive access for writes, basically. And that's this new project, which is called Capybara, Capabilities for Mutation. If you think a bit Australian accent, it's Capybara. So it's a bit like capabilities in borrowing, borrow checker sort of things. And yeah, that thing was generated from this picture, which is the earliest European representation of a capybara. So the tree is the Scala logo, and the banana is the Lambda. I quite like it. Okay, so just to show you what it can do, so we have a method for matrix multiply, right? So it has to be performant, so no matrix returned. It works on existing matrices, A, B, and R. But the question is, well, what is the input and what is the output? And what arguments can be shared and which ones must be unique? Those questions you have when you interact with these libraries, obviously. So the way we want to do this is we want to write it essentially this way, that we say our matrix class is a mutable class. That's the first thing we have to declare. And then those class would have read methods like apply for the index, and it would have update methods that change. And I have to mark these with update. And the final thing I have to do in the signature of the matrix, I have to say, well, Z is a matrix with a hat. So it could capture arbitrary capabilities, including the capability to modify the matrix. That's part of it. So hat means, among others, now can be modified. And in the new system, that requires an extension of our system that we're still working on. It also means this hat doesn't share with anything else that can be accessed. It's different from all other hats. It's different from all capabilities you can see. And that means that if you have now calls to this matrix like this one, then the bottom two will be errors. So you can't multiply M1, M2 with M2, because essentially the result would be the same as the second argument, and the same thing would be this thing here. Actually, no, it's just this one. This one is a typo, sorry. So that is sort of the simplest way I think you can approach this problem of shareability and exclusive access and read. So it's just a single hat on this thing that essentially explains you what that is. So I'm quite excited about the potential for it. It should be available in the next version of Scala, which will be Scala 3.8. So that's the ambition. So to conclude, I believe capabilities are extremely versatile in what they can do. They can model global effects such as I/O, control effects like labels, exceptions, async. They can give you permissions to execute an action or get access to data, and they can express mutations and sharing of variables or regions. So the main value proposition of Scala as a language, I believe, is that it's both safe and convenient. That's the ambition. And I believe with the right types, we can make capabilities also safe and convenient, using implicit parameters for the using classes and capture sets to model the retained capabilities. That's sort of the 10,000-foot view. Thank you.